Let's take a look at a related rates problem and see all of the steps we need to go through to get to a solution, and we'll go through them step by step. So I'm on page 295 in the workbook right now, and here's the problem we have. We have air is leaking out of an inflated balloon in the shape of a sphere at a rate of 230 pi cubic centimeters per minute. At the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? All right, so let's stop for a moment and visualize this problem before we go back to it. So I've got a balloon that's full of air and it's leaking out. All right, and it's leaking out at a constant rate because maybe it's got, I didn't tie the spigot end of it. So air is flowing out of the spigot end at a constant rate. But even though the volume coming out of the sphere is constant, the radius of the balloon is not going to be constant. All right. And so they're saying at the moment when the balloon is, this size, how quickly is the rate of change of the balloon's radius changing? All right. And so that's a problem we're going to be able to solve with related rates. Okay. Now that I've gotten that, let's go back to the paper. And our workbook is very friendly to us because they are giving us a step-by-step process for that. All right, so the first step is to identify all of the variables involved with the problem. All right, so we've got R, which is radius, and we're talking about air leaking out at 230 pi cubic centimeters per minute. What is that talking about? Cubic centimeters is a measurement of what? Well, it's a measurement of volume. All right. And so what we want to do is we want to identify which, if any, of the variables in the problem which remain constant. We'll see how that comes up later in later examples. But right now, none of those things are remaining constant. So the radius is changing as the balloon is getting smaller, and the volume is decreasing as air is coming out of the balloon. Okay, let's identify the rates that are given and the rate that we wish to find. Okay, so the rates that were given is we're given that. So how am I going to express that as a rate? Which variable is changing? Well, that's the change of the volume. So dV dt is equal to what? This is a little bit of a trick question. The air is leaking out. The balloon is getting smaller. The volume is decreasing. So I really want to write that as negative 230 pi. Okay, so that's the only rate that we're given there. And they ask us to find the rate of change of the radius. So we'll say dr dt is what we want to find. Step 4 is we want to write an equation that ties these variables together. Okay, and this time we're told that the balloon is in the shape of a sphere. So the relationship between the radius of a sphere and the volume of a sphere is V is equal to 4/3 pi r cubed. If you're not familiar with areas and volumes, I've got the geometry reference sheet in our Schoology page. So you can find volumes like this and surface areas and areas of plane figures and things like that. So that's kind of handy to have. All right, just rates all the variables which array is given for which array is to be determined. Substitute any value that represents a variable that's constant throughout the problem. It is important to keep in mind that you can have only one more variable than you have rates. You may have to make a substitution that relates one variable in terms of another. This is all things that will be important to keep in mind when we get to harder problems. But here we have two variables, R and V, and that's okay because we have one rate. So we've got two variables and one rate. So that's the right thing to do. The next step in step 5 is to differentiate both sides of the equation with respect to time. We did that on the previous page. Turns out I did it incorrectly. So I'm multiplying 3 times the constant. So that becomes 4 times pi times r squared dr dt. Okay? And so now what we want to do is we can substitute everything we know into this equation and then solve it for dr dt. So let's see what we've got. We've got dv dt is equal to negative 230 pi is equal to 4 times pi times r squared. And we're told that the instant that we're curious about is the one where the radius is 4 centimeters. Okay, so we're going to substitute 4 in for r. If we were thinking about this at a different moment in time, we could substitute in a different value of r and find the rate of change at that moment, dr dt. And now we've got this equation just in terms of dr dt, so we can solve that. Dr dt is equal to negative 230 pi over 4 times pi times 4 squared. All right, and the pi's cancel each other out. That was generous of them. And so I'll grab my calculator. And so negative 230 divided by 4 squared is 16. 4 times that is 64. And when you're answering questions on the AP, they like to see at least 3 decimal places of precision. So negative 3.594. And what's our units going to be for this? We're thinking about the change in radius over time. So that should be a unit of measurement divided by a unit of time. So our unit of measurement is centimeters, and our unit of time is minutes. So it's negative 3.594 centimeters per minute. Let's think about this for a second. Our rate of change is negative. Is that something that surprises us? Or in the context of this problem, does this make sense? That the rate of change of the radius of the balloon should be negative? Well, so what we've got is we've got air leaking out of the balloon. So the change in radius at every point along here is going to be negative because the radius is getting smaller over time. So a negative rate of change does sound entirely appropriate for this problem. And so we can say that at that moment, the instantaneous rate of change of the radius of the balloon is negative 3.594 centimeters per minute, and it's 4 centimeters at that point. So it would be out of air in just a little bit more than a minute, although it is continually changing that rate of change. So that's the kind of idea that we've got with related rates problems. We can have some basic formula, like the relationship between volume and radius of a sphere, and then we can implicitly differentiate that with respect to time and find that we can also talk about the relationship between the change in volume over time and the change in radius over time. We'll do more problems of the related rate sorts in the next video.